Hey guys, today's video is about naive Bayes. We'll go through an example. If you are not sure how naive Bayes works, please check out the previous video. Say, we have this database with attributes gender, age, and buying computer. Buying computer is the target attribute, so the goal is to predict whether a person will buy a computer or not. Specifically, we want to know if a 25-year-old female is going to buy a computer, and we'll use naive Bayes to make a prediction. Ci is the class of target attribute. In this case, there are two classes in the target attribute, yes and no, which represent buy and won't buy. X is the evidence or descriptive attributes. So this database has gender and age as evidence. In fact, this evidence X is fixed. We assign X to be female and 25-year-old, which is in the range of 18 to 50. We first look at the class yes. So the simplified version of Bayes' theorem becomes this. The class conditional independence allows us to convert the probability of 25-year-old female conditioned on buying to the probability of 25-year-old conditioned on buying times the probability of female conditioned on buying. So we just need to find the corresponding probabilities. Since we are dealing with class yes, we only need to look at people who actually buy a computer, and there are 3 people buying computers in our database. First, the probability of 25-year-old conditioned on buying computer is 1/3, because 1 out of 3 people is in the age range 18 to 50. Second, the probability of female conditioned on buying computer is 2/3, because 2 out of 3 people who buy a computer is female. Then, the probability of buying computer is 3/5, because 3 out of 5 people buy a computer. Therefore, the conditional probability is in proportion to 2/15. That is, given the subject is a 25-year-old female, her probability to buy a computer is in proportion to 2/15. Next, we deal with the class won't buy computer. The formula is the same as before. We just replace buying computer with won't buy computer. Again, we convert the probability of 25-year-old female conditioned on won't buy computer to 2 conditional probabilities, so we can focus on one attribute at a time. In this case, we only need to look at people who don't buy a computer. First, the probability of 25-year-old conditioned on won't buy computer is 1/2, since only one person is in the age range 18 to 50. Then, the probability of female conditioned on won't buy computer is 0, since both the people who don't buy a computer are male. Last, the probability of won't buy computer is 2/5, because 2 out of 5 people in the database don't buy a computer. Thus, the conditional probability is 0. In other words, it's impossible for a 25-year-old female not to buy a computer. Now we have the conditional probabilities for both classes, and we can compare the numbers. In conclusion, the model predicts a 25-year-old female will buy a computer, since the conditional probability of buying computer is higher. However, if you think about this, you may find it's not reasonable for a conditional probability to be 0. In this case, the probability of won't buy a computer conditioned on 25-year-old female is 0, because the probability of female conditioned on won't buy computer is 0. Although all the females in our database buy a computer, in the real world, there must be some females who don't buy a computer. It's probably because our database is too small and fails to record all combinations, and we shouldn't eliminate the possibilities just because we didn't see them in the database. Therefore, we use the Laplacian correction to solve this issue, and we'll talk about this in the next video. Alright, that's the complete example. Thank you for watching my video and see you soon.